Alright, so here we have what I would consider to be some very tricky integrals, or very tricky functions to differentiate because they involve integrals. So, the way that we want to do this is that if you sort of think about it, when you have an integral from a to x plus y, you can, well, this is a function of x and y, so you want to write it as a function of x and y. That makes it clear how it's sort of behaving. I did not explain that well, so let me show you what I mean. So we have x comma y equals the integral from some number a to the number x plus y of g. And of course we're in it, there should be a d something here, but so maybe the integral of g of t dt, integrating from t equals a to t equals x plus y. Now what we're going to do is we're going to define additional functions here to sort of help us work our way through this. So we've got, so here, if we, let's let alpha of z, where z is some number, just be the integral from a to z of g. And of course this is g of t dt, but I'm going to stick with what Spivak is doing here and not include the extra integral or extra notation, because you know what I mean by this. So alpha of z is the integral from a to z of g, and we're going to define beta of x comma y to be x plus y. Okay, so f of x comma y, well, we're integrating from a to x plus y. Well, x plus y, that's just beta of x comma y. So we can write this as beta of x comma y, and then of course we're integrating the function g. But now, if we can write this in terms of alpha, because if you plug something into alpha, it's just integrating g from a to whatever you're plugging in. So this is actually alpha of beta of x comma y. And so now we can sort of see how we would go about finding these derivatives. We would have to use the chain rule here in just a normal way. So if we want to be able to use the chain rule, we want to know the derivatives of these things. So alpha of z equals the integral from a to z of g. So if we take the derivative, I'm just going to write out, since alpha is just a function of one variable, I'm going to write alpha prime to be the derivative of alpha. So alpha prime, when you plug in z, well, this is the derivative with respect to z of the integral from a to z of g. And here we can use the fundamental theorem of calculus to prove that this is just g of z, because that's just like, that is the fundamental theorem of calculus. And then if you take the derivative of beta with respect to x, you're going to get 1 plus 0, which is 1. If you take the derivative of beta with respect to y, you're going to get 0 plus 1, which is 1. So d1 beta equals d2 beta, which is equal to 1. Okay, before I go on, I do want to rant a little bit about this use of the fundamental theorem of calculus here. I really don't like the way that these sort of... I don't think this is a really good exercise, but we really shouldn't be using an exercise involving the fundamental theorem of calculus until we've rigorously proven the fundamental theorem of calculus. And of course, like, this textbook is meant for an audience of people who have already taken calculus. And if you've already taken calculus, you've already seen the fundamental theorem of calculus. But just because you've seen it doesn't mean it's been proven rigorously and mathematically. And of course, it turns out this isn't really a problem. Like, you can prove that the fundamental theorem of calculus holds and everything, but maybe we should have held off on this exercise until we actually have proven the fundamental theorem of calculus. But whatever, it's not that big of a deal. So if we want to take the derivative of f with respect to x, we have to do the outside first, and then multiply by the derivative with respect to 1 of what's on the inside, which is beta of x comma y. Now alpha prime of beta of x, so alpha prime of anything is just g of that thing. So this is g of beta of xy, and we know that d1 beta is just 1, so it's just, this is our answer. And if we write out beta, this gives us x plus y. So there we go. So the main thing here is that you're using the chain rule to help you evaluate these derivatives that involve integrals. And so then we're basically going to do the same thing for the rest of these exercises. So let's see here. For the next one, we've got alpha prime beta xy times d2 of beta, but d2 of beta is also 1. So this is also going to give us g of x plus y. And that's part A. Alright, so now we're going to move on to B. So now we have f of x comma y equals the integral from y to x of g. So here we have to be a little careful. Alpha of x equals the integral from y to x of g, and beta of y is also equal to the integral from y to x of g. Now the thing here is that we're going to want to evaluate alpha prime and beta prime. And in order to evaluate beta prime, we need to use the fundamental theorem of calculus. But in the fundamental theorem of calculus, the variable is in the upper part of the integral. So we want to flip the y and the x here. And the way we do that is that we know from, well, if we had already studied integrals before doing this exercise, then we would know that if you want to flip the limits of integration, you have to put a minus in there. So this is going to be negative integral from x to y of g. Okay, and so now we can do alpha prime of x. Well, actually, what is d1 of f? d1 of f is just literally d1 of alpha of x, which makes sense. We want to write alpha as a function of x here because we're taking the derivative with respect to x. And so when we take the derivative of alpha, well, we just use the fundamental theorem of calculus, and this is going to give us just g evaluated at the upper time x. So this is just g of x, and then d2 of f, well, this is going to be d2 of beta of y. And so here, this is actually negative d2 of the integral from x to y of g. And so this is going to be negative g of y. And there we go. Okay, so now we have part C. So we have f of x comma y again. This is the integral from eta, and now we have x times y of g. And this is just going to be like part A, where we've got alpha of z is equal to integral from a to z of g. But here we're going to have beta of x comma y be x times y. And again, we're going to have f of x, y. So f here is equal to alpha composed with beta, because f of xy is equal to a alpha of beta of x comma y, just like in part A. So what we do now, well, do we even need to do that? No, we don't even need to do this part necessarily, because what we can do is we just start writing d1 of f is, so this is d1 of alpha of xy. So this is equal to alpha prime evaluated at xy times d1 of x times y. And alpha prime, we know from part A, is going to be just g evaluated at the upper integrals thing. So this is just going to be g of x times y. And when we take the derivative with respect to x of x times y, we just get y. So now thinking about this, I could have defined beta equal to x times y and done it that way, but I'm just sort of skipping over that explicit use of the chain rule, even though I made it more explicit in part A. That's not, strictly speaking, necessary. So again, d2 alpha xy, and this is going to be alpha prime of xy, which we know will be g of xy. Then we're going to multiply by d2 of xy. So we're going to, this time we're going to end up with x times g of xy. And that's it. Alright, so now we have part D. And what do we have here? We have f of x comma y is the integral from a to the integral from beta y of g of g. So here, what we're going to do is we're going to let alpha of z be the integral from a to z of g. We're going to let beta of z be the integral from b to z of g. So now f of xy can be written as, so we're going to integrate from a to, well, the integral from b to y of g is just beta evaluated at y. So this is from a to b beta of y of g, but this is alpha of beta of y. So this is alpha of beta of y. And so from here, there's no x's involved at all in this problem. So we know that d1 of f is going to be 0, but d2 of f is going to be, let's see here, we need alpha prime of beta of y times beta prime of y. And let's see here, so beta of y, so alpha prime and beta prime are just g of the upper limit. So let's see here, alpha, so this is going to be g of beta of y times g of y. And so this is going to be finally g of, and on the inside here we've got the integral from b to y of g, and then we multiply by g of y. And that's all there is to this part of the exercise, and I believe that's it. That is it. So now we are finished.